All right. So, the next topic that we're going to talk about in this module is the scientific method. So, a very, very common thing that will be said throughout this course and a lot of times when talking about climate change is we'll say, well, it's a sound science. But what does that actually mean? What does it mean for science to be sound? Like, what is science anyway? And so that's what we're going to delve into in this module, and then a little bit, or in this video, and then a little bit in the next video as well. So let's jump in. So first off, what actually is science? I'm sure many of you have heard about or have heard the phrase science used so many times and in many different definitions. Like it comes down to a science, or science is my worst subject. I hear that one a lot. But what actually is science? Well, a lot of times when we think of science, we think of old white men in lab coats, or we think of people who are mixing test tubes or mad scientists and so on, kind of like in the little picture here. But what actually is science? Well, science is defined as the systematic study of the world around us through observation and experimentation. There's a lot to unpack there. Um, really, in layman's terms, though, science is the study of everything. So, contrary to popular belief, you are actually a good scientist, whether you think so or not. Yes, believe it or not, you are a good scientist because we're curious beings and we try to figure things out. Whether it's learning how to walk, trying on clothes to see if they fit or how they look on you, um, trying different drinks at Starbucks to see which one is your favorite, going to a brewery and getting a tasting flight and trying a few different beers before ordering a pint of something. That's one of my favorite. Um, those are just a few examples of collecting data and studying the world around you, whether it's the world of beer, whether it's the world of the best route to get to school, whether it's whatever it is. And there's two main ways that we do this, and that's through observations and experimentation. Observations and experimentation. And those two things are kind of the same thing in a way, but there's a big difference between the two. So let's talk about them. So, observation. An observation is simply collecting data without changing anything, without actually manipulating anything, without actually influencing anything. So, for example, if I go outside with a thermometer and I hold up the thermometer and I measure the air temperature, what I have just done is I have just made an observation. Or if I go outside and I look at the sky and I go, oh, it's partly cloudy. That's making an observation. I'm not changing anything. I'm not influencing anything. Another example, I kind of like to do this for fun sometimes when I walk into a classroom, is look at how many students are on their cell phones. And it's usually somewhere around 75%. And that's what I've found is roughly 3 and 4 students before class are on their phones. Guilty, I would be one of those students. Um, and I'm not saying or doing anything. I'm not changing anything. I'm not influencing anything. All I'm doing is just looking. I'm just collecting data. I'm just collecting information. Now, that differs from experimentation. Let's actually use the cell phone thing really quickly. If I suddenly made a comment and said, wow, a lot of you are on your cell phones. um, Not that I would do that because that sounds kind of judgy, but let's say I did do that. Wow, a lot of you are on your cell phones. A few people would probably feel a little shame and would probably put their phone away. Or maybe they wouldn't feel shame, but they would feel like, okay, the teacher is passing judgment or something like that. Again, I wouldn't do that. But, and then a few of them would put their phones away. What I have just done in that situation is I have just manipulated the environment. I haven't made I haven't just come in and done nothing. I've actually changed the environment. I made a comment. I made a statement. And that statement caused some people to react. And then the reaction is then observed. I noticed that, okay, half the students put their phones away or something like that. And that is an experimentation. What I've just done there is I've just manipulated the situation. I've actually changed the environment. I introduced a new variable into the environment and observed the outcome. Um, Another example I love to say is the effects of alcohol on test scores. Let's say I had a class do a test, and then I took all the students who were over 21, got them liquored up, and then did another test. Maybe I do the exact same test so that doesn't change. But all I've done is I've introduced something into the environment that caused a change. That's experimentation. And then I observe the outcome. So when I said earlier that the two things are kind of the same, what I mean is that in both of them, observation occurs. The difference is with experimentation, I add something, I change the environment, I do something to change it. I introduce a new variable, whether it's a comet, whether it's alcohol, not that I would do that, whether it's caffeine, whether it's um, changing the temperature in the room, whatever it could be. I've done something to manipulate the situation, and then I observed how that changed the situation. Um, Weather forecasting is an example of that. We model our planet Earth, we change something in it, and then we watch how it evolves. And that creates what's called a forecast. Regardless of whether it's an observational study or an experimental study, both of these follow the scientific method. The scientific method is simply the sequence that scientists use to do science. And I would bet you a nickel that most of you have heard of the steps of the scientific method, even if you don't remember them. But there are 6 main steps to it. And the 6 main steps are: first, you have to identify a problem. Believe it or not, this is the hardest of the 6 steps. Figuring out what you're going to do. Figuring out what you're going to look at is by far the hardest problem. Once you've identified a problem, though, you then propose a hypothesis. A hypothesis, the 2-word phrase that's commonly used for a hypothesis is an educated guess. Basically, what you're doing is you're making a prediction based on what you already know. Now, I'm going to talk a little bit about hypothesis and how it differs from the word theory in a few minutes. But a hypothesis is simply an untested, unproven, based on background knowledge and nothing else, guess as to what's going to happen. You then design a study to test that hypothesis. And maybe I shouldn't use the word experiment here. Even though it is an experiment, it could be an observational study or it could be a manipulative study where you change something. But basically, what you do is you test that hypothesis. It has to test the hypothesis. What I mean by that is that whatever you're studying, whatever experiment you're doing, has to revolve around your hypothesis. For example, if I wanted to know when the warmest time of day is, what time of day is the warmest? My experiment probably should focus on measuring the temperature during the daytime. Right? If I was measuring the humidity during the daytime, that's all well and good, but that's not testing my hypothesis because that's just telling me when it was the most humid, not when it was the warmest. Does that make sense? Yeah, your experiment needs to test your hypothesis. Now, once you run your experiment, you're going to get results. You're going to get data. And that data is then the next part of the experiment or of the scientific method. You collect and organize results. You put them in tables, you gather them from the experiment, you talk about them. Now, here, all that you're doing is you're just collecting and organizing the raw data. You're not doing anything to the data. That's the next step. The next step is called analysis. Here, you actually try to see what the data is telling you. You do this by taking averages. Let's say I wanted to find out the warmest time of the day. And so I collected temperature data for 30 days. And then I took the average temperature at each hour. And then I looked at when the warmest temperature was. Now, that would probably not be the best experiment. But I would just look at when the warmest average was. There, I averaged the data out. I performed a statistical analysis of the data. And this is where statistics comes in. Don't worry, we're not going to do a lot of statistics in this class. But things like taking the averages, looking for trends, also asking the question, does this data make sense? And then at the end of your analysis, you then have an answer. And the answer is, was your hypothesis true or not? And that brings you to your conclusion. One of two things happens here. Either your hypothesis passes or it doesn't pass. Can't say that it fails, but it doesn't pass. So it either passes or it doesn't pass. Either the data supports the hypothesis or it does not support the hypothesis. If the data supports the hypothesis, you now have proof that the hypothesis is true. When that happens, the hypothesis actually gets an upgrade. It becomes something new called a theory. Contrary to popular belief, theories actually have a lot of backing to them. They have a lot of evidence behind them. They have a lot of support behind them. I'll talk about that in the next lesson. But that's what happens if a hypothesis is checked out and is proven to be true. One of the things about the scientific method is it's not rigid. These 6 steps do not have to happen in perfect sequential order. Even though it's a sequence, they don't have to happen in perfect sequential order. Let's say you're running an experiment and something completely different and new happens. That's good. But that changes your experiment. Maybe you find something out by accident, which, by the way, some of the biggest discoveries in history, such as rubber, penicillin, the microwave oven, were actually discovered by accident. But, or let's say funding changes. Unfortunately, that happens. And when that happens, you have to change your experiment. All of that to say, the scientific method is very flexible. But it's actually worth saying that it's also much more complicated than what it sounds like. It's not this perfect, beautiful, linear progression, but rather you're constantly bumping back and forth between different activities. Whether it is communicating your findings with others, whether it is investigating what is already known, whether it is defining the problem, figuring out what you're actually looking for, carrying out the study, um, reflecting on the findings. At the end of the day, these all center around questions. And questions commonly change what you're looking at. So if you look at a bunch of data and that something keeps showing up on the data that you didn't expect, that could change your experiment. Or let's say you've carried out your experiment and then you try to publish it. And as you publish, or as you're working on publishing it, and it's going through what's called peer review. Let's say one of the peers finds a glaring hole in your work and says, "Yeah, but you didn't do this. You need to go do this before you can come to a sound conclusion." Well, guess what? It's back to the drawing board. You have to either refine your hypothesis or, at the very least, refine your experiment. All of that being said, the scientific method revolves around questions, and it is much more complicated.